In this video, I will draw the mechanism for the acetoacetic ester synthesis, but I think maybe the more important thing is to see its similarity to the malonic ester synthesis. Truly, if you really understand the malonic ester synthesis, this is almost the exact same thing. So what we're going to do here is we're going to take an alkyl halide, so we have this new chemical statement. Remember, you could read this left to right or right to left. This one sentence has two statements in it. If you read it right to left, what it says is you can take an alkyl halide and make something called a methyl ketone. And you'll notice this is a ketone. It is a carbon double bonded to oxygen with a carbon on both sides. And one of those carbon groups is a methyl group. So it's called a methyl ketone. So we're making a methyl ketone here. And so you can use an alkyl halide to make a methyl ketone. That's reading this right to left. Reading it left to right. Reading it in the reverse direction, what it says is if you want to make a methyl ketone, you could make it from an alkyl halide. So either way, whatever your focus is, you can make this transformation happen. Now, if you notice, this is almost the same exact thing as the malonic ester synthesis. It's just in the malonic ester synthesis, this methyl group was an OH. That's the only difference. And indeed, the recipe to do this is almost exactly the same thing. We still have sodium ethoxide and ethanol as our first step. We still have an alkyl halide as our second step. And we still have aqueous acid, so hydronium, and heat as our third step. The only difference is the molecule we begin with, and this is really, really similar. You still have the three sort of carbons with the two carbonyls. You still even have one of the ethyl groups of the ester in there. The only difference is instead of an OET on the other side, you have a methyl group. And so this is the group that's going to be added onto the alkyl group, and the mechanism will really be exactly the same. Now the name for this molecule that's taking the place of diethyl malonate is Ethyl Acetoacetate. So an aceto group is just a sort of old common name for having two carbons. And so you have this aceto group, two carbon group, with an acyl group there. That aceto group on an acetate, so another two carbon aceto group with an ethyl group on it, so ethyl acetate. So you have an ethyl group and an aceto group on this acetate molecule, so it's ethyl acetoacetate. Okay, well, if you compare that to the malonic ester synthesis, you'll see they're really, really similar. The only difference, notice, is you have a methyl group instead of an OH in terms of what you're making. So you're making a methyl ketone rather than a carboxylic acid. Notice how similar these recipes are. The first steps are the same, the second steps are the same, the third steps are the same. Even the original molecule you have is almost the same. The only difference between ethyl acetoacetate and diethyl malonate is this group at the end. Instead of an ethoxy group, you have a methyl group. And that's the only difference. That and the product, that methyl group shows up in the end, so you have the methyl group there instead of the hydroxy group. Otherwise, the reaction is almost exactly the same. Now, we can walk through the mechanism. We will. I think it's a good exercise. But you'll see that it's really the same mechanism as for the malonic ester synthesis. And so maybe if you wanted to review that, this is a great review for that. That's another way you could use this video to review how the malonic ester synthesis works, because it's pretty much the same way. So the first thing you start with, we're going to start with ethyl acetoacetate. So we still have the OET. We still have those three carbons, but instead of an OET on the other end, we just have a methyl group. And we have the carbonyls, three carbons away from each other. So one carbon is 1 and 3 to each other. Now we treat that with sodium ethoxide, and it does have to be sodium ethoxide because we still have one ester. Now this is going to function as a base, but we still have one ester, and this can undergo a nucleophilic acyl substitution. This could theoretically attack that carbonyl carbon, kick the pi bond up, you get the tetrahedral intermediate, and then it would kick down, and it might expel this original group. Now, if this is the same, then the molecule won't change overall. But if you used a different base, then it could change what this group is, which we don't want to do. So we used sodium methoxide and ethanol for the same reason we did in the malonic ester synthesis, so that if it does function as a nucleophile here, it won't change the molecule. There's another thing it can do, though, and this is what we want it to do. It can steal the acidic alpha hydrogen. So if it does a proton transfer, and that electron, the electrons that were holding that hydrogen on, snap back onto the alpha carbon, then we create a carbon nucleophile on our ethyl acetoacetate molecule. So zooming in on that molecule, focusing on that, that now has a lone pair on that alpha carbon, and you'll notice that this carbon is alpha to both of these carbonyls, which means that this exists in a p orbital, and there are p orbitals on both of these because of the pi bonds, and so these are all parallel p orbitals. The electrons can spread out over all of them, all 5 of those atoms. And so it's spread out and stabilized by being diluted in space. Okay, well, now that we have a nucleophile, what can you do with a nucleophile? Go back to the classics. You can do a substitution reaction. And this is where this alkyl halide comes in. You treat this with capital R, that's any carbon chain, capital X, that's any halogen, so that's going to be functioning as a leaving group, so chlorine, bromine, iodine. Our nucleophile can swoop in, attack that carbon, and kick the leaving group off. Notice that because this is an SN2 reaction, this carbon needs to be either primary or secondary. The reaction won't work if it's tertiary because this substrate will be too crowded. That's the hallmark of an SN2 reaction. If that doesn't sound familiar, let me know. I'll send you a video from Organic Chemistry 1 that walks through that concept. So after you do that, and here what we have happening are 2 things. We have nucleophilic attack, that's this here, and then we have loss of the leaving group, this here. Okay, so when we have that SN2 reaction, what we end up with is this same molecule, but instead of having that lone pair, we have the R group attached there. And so that's that second step. First, you created the carbon nucleophile and the alpha carbon by adding a base. Second, we add an alkyl halide to do an SN2 reaction. Now, when we add this, first let's think about adding this H3O+, the aqueous acid. That's going to hydrolyze this ester. So that's from the carboxylic acid derivative chapter. If you treat that with aqueous acid, you do an acid-catalyzed hydrolysis of an ester. Now, there are several videos on the mechanism for that from that chapter, the carboxylic acid and carboxylic acid derivative chapter, and you drew that mechanism on a previous test. Ultimately, you protonate the hydrogen, water comes in as a nucleophile, you get the tetrahedral intermediate, you stabilize the water that comes in by taking another hydrogen off it, so it turns into an OH. The tetrahedral intermediate comes back down and kicks this off. There's another proton transfer that turns this into a better leaving group first. But because this video will be long enough by itself, I'm going to just refer you for that mechanism for the hydrolysis of an ester to look at the playlist for carboxylic acids and their derivatives, and you'll see there's a video that explains how that happens in there. Okay, well, now that we have this, we can use heat. And heat is going to do a decarboxylation. This is going to leave as carbon dioxide. Now let me redraw this so that you can sort of see step by step how that would happen. So I'm going to redraw this sort of to the side. This carboxyl, I'm just going to rotate this bond so the carboxylic acid is pointing up. Oops. So that's this carboxylic acid. Now we have the carbon there and our carbonyl, and we have the R group. Okay, so I drew this so that we can sort of see connections here. This is going to react through a pericyclic reaction. Let me draw charges in so that you can sort of see why these electrons are moving. These positive charges are places where electrons are being lost to electronegative atoms nearby. Okay. Now, these electrons in this pi bond are attracted to that positive charge there on the hydrogen, so they try to snatch it away. But it's being tugged by these electrons. So if this loses that, where do these electrons go? Well, the closest positive charge they have here is this positive charge on this carbonyl carbon. But that carbon already has 4 bonds, so it would have to lose these. These electrons here at the same time go to fill the gap that these leave behind when they leave. They go toward this slightly positive carbon there. So you have all those electrons moving in a circle. You'll remember that's a pericyclic reaction. And so to draw the products there, I'm going to copy and paste that molecule. You can refer to the one on top. I'm going to redraw these bonds. This bond breaks and forms a new pi bond between the oxygen and the carbon there. This sigma bond breaks. And goes to form a new pi bond between these carbons. This pi bond breaks and goes to form a sigma bond to this hydrogen. And so we have 2 things here. Notice that we have a carbon dioxide on the left. That's this carboxylic acid got turned into carbon, double bonded to 2 oxygen, so carbon dioxide. It looks weird here because it still kind of looks like our original drawing. But once it leaves, it becomes linear, so you have carbon double bonded to 2 oxygens, carbon dioxide. And then we have an enol. Now, if you remember from the first 4 videos in this chapter, and also from Organic Chemistry 1, enols, molecules that have both an alkene and an alcohol attached to each other, tautomerize, which means just one hydrogen moves its position and electrons accommodate it, and that tautomerizes to give you the ketone. So notice that what we've added to our R group are 2 carbons and a methyl ketone. So it's very much like the OH in the carboxylic acid that we added in the malonic ester synthesis. It's just instead of an OH, we have a methyl group there. All of these steps are the same as in the mechanism for the malonic ester synthesis. It's just we're starting out with ethyl acetoacetate, a molecule that has a methyl group at the end, and so we attach a methyl ketone to our R group, as opposed to in a diethyl malonate, it's an ester, this hydrolyzes, and so you have a carboxylic acid in the end. So that's the mechanism for the acetoacetic ester synthesis. We'll walk through how to think through this exercise, how to think through this reaction in the context of synthesis questions in the next video.